Okay guys, so today I'm going to show you why the integration, the definite integration of from A to B of a function, I'm going to call this with respect to dx, it's going to be equal to that summation, right? This is f of x. I'm going to say capital X, capital F will be the antiderivative or the integral, and lowercase f or little f of x is the derivative itself. So this is the integration of this, and this is the differentiation of this. So this is going to be f of x plus c, but we're not going to worry about the plus c right now, just the f of x. Okay, and what does this mean, the definite integral? Definite because it goes from a to b. Okay, you can have an indefinite integral, which is just the integral, or you can have a definite integral, which is from a to b. This is going to be f of x, right? Well, it's going to be actually f of x, where x is b, minus f of x, where x is a. This is going to be the same thing of that summation from I is equal to 1 all the way to n, right? Where n approaches infinity of that, those things that we did, right? It's going to be delta x times I minus 1 or times I. This is the left endpoint. This one here is the right endpoint. The whole thing is going to, as n approaches infinity, delta x is going to approach 0, okay? And delta x is the width of those rectangles, remember? All right, so I'm going to show you guys why this is true. This thing is called the first fundamental theorem of calculus. It's very important, you know, mathematicians, I mean, real mathematicians with PhDs and stuff, they say that it's probably one of the most important theorems there is in mathematics. Okay, so let's start with that saying. Let's just say that you have a function s of t. So this is a function. It's a function of space with respect to time. Okay, it's a function of space as a function of time. So you give it a time, you're going to get a space. And then if you differentiate this thing with respect to time, you're going to get the instantaneous velocity also with respect to time. Okay, so let's see how that works. If you have here, so this is going to be time, and this is going to be here I'm going to put the velocity with respect to time. Let's just say that the velocity is constant, okay? So for the velocity to be constant, we're going to do this. And here you have an A, and over here you have B. Let's say that B equals 3, okay? This equals 3 and A equals 0. All right. Now, let's just say that this value in here equals 5. This is 5 feet per second. Okay, so what's the total amount of space that the car went? Okay, so it had 3 seconds. Okay, this is time in seconds, and this is the velocity in feet per second. So it went always at 5 feet per second. In 3 seconds, what do you have? 5 times 3, 15 feet. Okay, now look at this. Here you have 3. I know that's it's not to scale because the 3 is larger than the 5, okay, but just bear with me. This is the 3 and this is 5. So what is the total area of this rectangle here? 3 times 5, right? Okay, 3 times 5. How did you know that? Well, you see, all you gotta do is you also gotta think that in order to fill out this whole thing, you get this plus this plus this plus this plus this, infinite amount of infinitely narrow rectangles, right? You're going to have all these rectangles summing up, and you're going to get the whole thing. That's great. Now, okay, so when you find the area underneath this graph in here, you got to remember that velocity is the differentiation of the velocity function is the differentiation of the space function. So the space function with respect to time is going to be f, the big F of t. And the velocity with respect to time is going to be the little f of t. Okay? So this is the differentiation, this is the integration. All right. What did I just do here? Here we just made the summation, right? One plus another plus another plus another. So you made all the summation of all these small rectangles and you got the area. Okay. Having that area, what did you get? You got 3 times 5, which is 15. 15 what? Well, you got 3 seconds times 5 feet per second, okay? And here you have dimensional analysis, so this seconds cuts with this second, and you have what? 15 feet. So what is this? Feet. It's a unit of space. It's not a unit of velocity, it's not a unit of time, it's a unit of space. So you see that when you find the area under the graph of the derivative equation, you get something that's related to the antiderivative equation, to the integration equation. Okay? So the area under the graph of the derivative is going to be related to a magnitude that's related, well, the area under the graph of the derivative is related to the magnitude of the integration. So you're going to plug in this 15 feet over here. All right. Now, how do you get 15 feet? How do you get 15 feet? Well, you see, that means that if you do what, there's something else that I want to show you guys. At 3 seconds, the car had run 15 feet. Okay, it's not pursued, got to a distance of 15 feet. At 0 seconds, the car got to a distance of 0. So what do we have here? We have that S3, okay, minus S0 is going to be 15 feet. Now look at this format, okay? What do you have in here? We have that the antiderivative of b minus the antiderivative or the integration of b at b minus the integration at a is going to be equal to the summation, okay, of I is equal to 1 all the way to n of the differentiation formula, of the derivative formula, which is going to be f of t, okay, times those infinitely small rectangles, right? Because the rectangles are going to be so thin, they're going to be infinitely small and smaller and smaller and smaller and smaller. So you see, you can say that because in here we don't have delta x, guys. Here's t, so we have delta t, okay? We can say that delta t as it goes to 0 becomes what? As this goes to 0, this whole thing equals dt, okay? Which is a very small amount of change in t. So you can say that it's the derivative at point t times dt. So it's going to be, because it's I, you have ti here, okay? And the dt is going to be the same everywhere because the widths of the rectangles are the same, all right? So now we have to prove this thing here. What I'm trying to do for you guys is to connect the dots, okay? So you have the differentiation of the space function with respect to time, and the space function is a function of time. Velocity is also a function of time. Okay, now the velocity was always 5 feet per second. So it doesn't matter what the time was, the velocity was 5 feet per second. Okay, when you integrate the velocity, what do you have? You integrate this with respect to t, because you differentiated it with respect to t. So what do you have? You're going to have the space thing, which equals 5t. Okay, now you get this t at 3, so it's going to be 5 times 3 minus 5 times 0. You get that 15 feet that you were looking for. So get in this 15 feet is the same area under the graph in here. All right. So you start connecting the dots in here. So you have this infinite summation over here in this graph. Okay. And this infinite summation of small rectangles is the integration at b minus the integration at a. So let's try to prove this formula here now. I'm going to erase everything else except this formula. I'm going to move this up here. All right. Let's try to prove that. I could prove this way, but I think it's easier to prove it this way. All right. So look at that. You have f of b minus f of a. Right. Now b is gonna be the n. It's gonna be this n in here. Okay. A will be 1. B will be n. Okay. Now for I to get to b, since you have infinitely small rectangles, infinitely narrow rectangles, for I to get to b, I is going to have to reach infinity. Okay, so a is going to be equal to I at 1. Okay, b is going to be equal to I at infinity. Because I is going to have to reach infinity to get to b. Okay, b is the final point. Why? Because you have a here, right? This is a line, then you have b, and then you have infinitely narrow rectangles in here. Look at that. And you keep going, and you keep going, and you keep going, and you keep going, and you go. You're going to have infinitely narrow rectangles and an infinitely large amount of rectangles, and you sum all of them up and you get from a to b. That's why I reaches infinity to get to b, and I is equal to 1 for a. Okay. Now let's see this here. F of b. Okay. F of b. Because, okay, let me just think in here, how am I going to do this? I'm going to say that this is x to the n, okay? X sub n. Or I, it could be I, yeah. When I is equal to n, right? And n is approaching infinity. Yeah, I can say, you know what I can say? I can say that here, I can say that here, I is actually n, and n is going for infinity. So here you have f of b. Let me see here. I'm just thinking about the notation, okay, to make it easy for you guys to understand. I can say that this is f of n. Okay, f of x sub n, okay, which is b, and this is a minus, right? I'm going to put the minus way over here. Minus, oh, that's not so much. Minus f of a. What is a? Is when x has an index of 1. So x sub 1. Okay. All right. So you have that. Why am I doing it like this? Because you see, what I can do is to say f of x sub n, and then I can do minus f of x n minus 1 sub n minus 1, but since I added this stuff in here, I gotta take it out because I still gotta do f of b minus f of a, okay? So you add in here f x sub n minus 1. And then you're gonna keep doing that. For example, plus, okay, as a matter of fact, minus f of x n minus 2 plus f of x sub n minus 2, right? And then you're gonna give I'm gonna put ellipses here, and what are you gonna have in the end? You're gonna have in the end minus f of x sub n2 plus f, I should have put this a little bit here, f of x sub 2. So minus f of x sub 2 plus f of x sub 2. Okay, so for example, this one's going to cancel this one, this one's going to cancel this one, this one's going to cancel this one, and you still have f of b minus f of a. I didn't alter anything, right? Okay, now look at that. You know what you can do? I'm just going to drag this thing here. This is what you can do here. You can multiply this whole thing by delta x, right? And you can, since you're multiplying the whole thing by delta x, you got to divide the whole thing by delta x. So you can get these two, and you can divide them by delta x, all right? And you can get these two, and you divide them by delta x, and you get those two, and you divide them by delta x, right? And then you have these two right here. This, whatever this is here, is going to be divided by delta x. And then you have this one, and you divide it by delta x. So this delta x is simplifying with this one, and this one is also simplifying with this one. So you can cut all these delta x's in here. I still didn't alter anything in the entire equation, in the overall equation. Okay, now what I can do is to find the limit, okay, of all these things as delta x goes to 0. As delta x goes to 0, this n in here is going to grow to infinity, right? Which is what we have here. Okay, so what is that? Look, you see what you have in here? You have f of x sub n, which comes to the right. Okay, we can also do it to the left, but let's do it to the right. So you have in here an x in for example, x of whatever. You can say k, okay? And the next x is going to be here, which is x sub k plus 1. Now look at that. What am I doing? The distance between them is delta x. Now, as delta x approaches 0, this point right here is going to keep coming. I'm going to put a different color here, like a blue. It's going to keep coming here, come, getting close to x sub k. What is that? That's the differentiation. You remember that stuff? What is differentiation? Okay, the derivative of f of x is going to be equal to the limit of f of x plus delta x minus f of x divided by delta x as delta x approaches 0. That's what we're doing in each one of these terms in here. Okay? That's what we're doing. So it's going to be the differentiation here, differentiation here, differentiation here, differentiation here. So what is it? And it's the sum of these differentiations. So you got a plus in here, you got a plus in here, you got a plus in here. See? So what do you have in here? You have the summation, okay, from I equal to 1 all the way to n approaching infinity, okay, of, I'm going to say f of ci, and I'm going to show you guys what the ci is, times, so this is the differentiation, okay, so this term in here is one of these terms, right? And this other term is another term in here, because you can see that this is a summation, right? So these are actually a bunch of terms, times delta x, which is this delta x in here, as delta x approaches 0. So it's dx. Alright, so you have the summation in here. Now what is this c? This c is, because you see from x sub k to x sub k plus 1, you have a space in here. So c is going to be one of these spaces, okay? And then you're going to say, okay, so this is not going to be precise, right? Because if I take a c in here, this is going to be the value. Let's just say that here's the x-axis. So if I take the c in here, it's going to have this value. If I take a c, hold on. This is the x-axis. If I take this c here, this is going to be the value. If I take a c here, this is going to be the value. If I take a c here, this is going to be the value. But it doesn't matter, because these things, the delta x is approaching 0. So you can see that every single point in the graph is going to be touched. Okay, this thing is going to get close. This point here will get close to this point here. Okay, and c is going to be squished between them. So you're going to have a c. Look, I'm going to put in green now. You're going to have a c here. You're going to have a c here, a c here, a c, a c, a c, 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 c. You're going to have c's everywhere. So you don't have to worry about that. Okay, so since this ci in here is actually in the end, as n approaches infinity, okay, as n approaches infinity, as the thing is going to touch every point in the graph, you can just say that this summation, okay, this summation in here is going to be the integral of f of x dx. And there's the proof, okay. This, I know it's kind of far-fetched to go like, what? But you have to think about this whole video from the beginning. Go back to the video, see that I was talking about the derivative of s of t with respect to t, okay, and I got the velocity with respect to t, not with respect to t, but as a function of t. So you have the derivative of the function of the space as a function of t with respect to t, which equals this. So this way is differentiation. Going back, okay, this way is integration. So you can see that when you integrate, you relate to that stuff. So you can see that the integral, okay, of v as a function of t with respect to t from a to b, from ta to tb, is going to be equal to the s of b minus the s of a. And what is the s? This is the integral, okay? That's why I started with this formula here. Look at that. What did I say? I said that we had to prove that f of b minus f of a, okay? F of b in the beginning was this term. F of a was this term in here, okay? So you can see that f of b minus f of a is going to be the summation of the derivative with respect to time, and that's what we got in here, okay? Look at this, except that I changed, right? I changed from t to x, but it doesn't matter. The idea is the same, okay? I was able to relate this thing here with the infinite summation. And here you have the infinite summation, and the infinite summation is the integration. Why the integration? Because you see that the infinite summation, okay, was going to be this one plus this one plus this one plus this is the infinite summation. But guess what? this relationship, this real-time relationship that we have with the space formula and the velocity formula, we're able to show that if you make the integral of the derivative, right, it's this thing, it's this mess in here. Look, the integral of the derivative with respect to the variable of differentiation, whatever it is, x or t, was the antiderivative at the last point minus the antiderivative at the first point. The integration at the last point minus the integration at the first point. So it's really confusing, guys. Whoever came up with this is a genius. I think it was Heman. His name is Heman. I'm going to write his name here. I'm going to erase and hold on. This is his name. He's a German. Okay. I think that's what's called Heman sums. Okay, that's the name of the guy that came up with this idea. I mean, if you just read it in a calculus book, you're going to come up with this. So there's the proof, okay, that now we don't have to keep making all those sums of n, right? 1 divided by n squared plus n plus 1 divided by n squared plus n squared divided by n squared as n approaches infinity. Now we can just use the integration. Now what proves that this whole thing is related? It's this whole context, okay? I wanted to prove that this was related to the infinite sums, and I was able to do over here in this part of the screen. I was able to prove this thing. Okay, now even if you have an infinite sums, who said that this is the same as the integral? Okay, well, relating the infinite sums with the integral is this part of the screen here. Okay, because we just saw that what happens, for example, in terms of the derivative of the space with respect to time. Okay, so I want to show you guys something here to make this even clearer. I want to show something here. Okay, now I'm gonna try to make this as much as equal as possible. It's not gonna be perfect, guys, but this is just something. This is point A, and this is point B here. This is time, okay, and this is velocity. Think about for a second, okay, because remember when you have during 3 seconds a velocity that doesn't change, okay, let's just say that you have a constant velocity here for 3 seconds. What's going to be? It's going to be 3 seconds times the velocity. Let's just say the velocity is 1, so 3 times 1 is 3. So this whole area here is going to be 3. All right? Okay. Now, let's just say that the velocity is changing. So you have a velocity here of, I just want to put like 4. This velocity here is 5. This velocity is 1. I don't know. I know it's not to scale. This velocity is 6. Okay. And this velocity here is 2. Okay, just pretend, right? And each one of these seconds is 1 second. Okay, each one of these spaces is 1 second. Pretend that it just jumped instantly from one velocity to the other. I mean, it didn't increase like this. Just pretend that it jumped, okay? So, what do you have for 1 second? You have 4. What do you have? Okay, well, let's see. Let's use the left endpoint. So, you begin here, okay? So, what do you have for the first second? 0. And then, what do you have for the second? You have 4 in here, okay? It's this. So, you have 4. What do you have for the third second? You have 5. What do you have for the fourth second? You have 1. For the fifth second, you have 6. And for the 1, 2, 3, 4, 5, for the sixth second, you have 2. Okay, so you were during the first, from this point in here all the way to here, okay, what was the space that you ran? Well, you ran 4 feet per second. Okay, in here you had 4 feet per second for 1 second. So it was 4 feet plus 5, 9, plus 1, 10, plus 6, 16, plus 2, 18. So from this point in time to this point in time, you ran 18 feet. All right. Now, this is not going to be very precise, is it? Because you don't jump from 0 all the way to 4. I mean, during this whole space in here, you're stopped. And then when you come right here at this point, you jump to 4 seconds. This is not very precise, but it's okay because you're going to make these rectangles in here, okay? You're going to make these rectangles in here become infinitely narrow. They're going to become narrower and narrower and narrower and narrower. So what do you have? You have the summation from I is equal to 1 all the way to n as n approaches infinity of what? Of vi dt. Okay, dt because this space in here is becoming very small. And what is vi? Well, it's going to be the velocity of 1 plus the velocity of 2 plus the velocity of 1 plus the velocity of 2 plus the velocity of 3 plus, you keep going, the velocity of n. This whole thing is being multiplied by dt. And what is v? V is the derivative, okay? So v is the derivative, is going to be f of, let's say, since you're going from front to back, from here all the way back here, okay, it's going to be the derivative of the time n minus time t n, function of time sub n minus the function of time sub n minus 1 divided by delta t as delta t approaches 0. This is going to be the derivative, okay? And what do you have here? The velocity. And what is the velocity? The velocity is the derivative of the space function, okay? So you see, can you connect the dots here now? Okay, so you're adding all these derivatives. If you're adding all these derivatives, you're doing this. I is equal to 1 all the way to n, okay, of what? Of the derivative at ci. Ci is going to be a number within this space in here, and then another ci within this space of dt. Okay, you're adding all these things together, and I just proved that is equal to what? It's equal to the antiderivative, okay? F of b minus f of a. Now, what is the antiderivative of v? Look at this. The antiderivative is s. So this whole thing here is going to be equal to, in this case, right? Because we're talking about v here, so it's going to be s of b minus s of a, okay? So I hope you guys can see it. I know it's very confusing and it's like, oh geez, okay? But that is you remember, there's something else too that proves that integration is related, okay? This is the proportional thing. I don't know if I'm gonna put related like this, but this is related to summation. Because, yeah, what did we say that was remember when we had a graph like this, okay? What did we say that it was going to be? The summation of all these things in here. The summation of all these things was going to be, the area. What's the area in here? Was going to be the summation, okay? So the summation is what you have. There's something else too that I want to show you guys. Pretend that you have this is t and this is velocity with respect to t. It's funny. And then I want a fixed thing, okay? I want a fixed thing here. This is 5, and this thing here is 3 times 3. Okay. What the velocity is not changing, right? Now, what is the antiderivative of the velocity? The antiderivative of the velocity is going to be s of t, which because the function is just 5, so the integration that's going to be 5t, right? Because we're integrating with respect to t. So there you go. So what do you have? You have y equals 5t. What is this, guys? This is the function of a line, of a straight line. Okay. So if you have this, now here you have time, and over here you have space as a function of time. So at t equals 0, what are you going to have? 0. It's right here. At t equals 1, which I'm going to put here, what is the function, what is going to be the value? It's going to be 5. So let's put kind of like here. Okay. And then at t equals 2, what's going to be the function? It's going to be 10. Let's just do this. Okay. And at t equals 3, what's going to be the space? It's going to be 15, because 5 times 3, 15. So we go kind of here, okay, because I have to make a line. So, and then you make a line in here. Okay, so yeah, this is not going to be too perfect, guys. It'll be kind of like that. It's because I'm not a robot. It's supposed to go through all these points. Okay, I'm just going to do this here, and I'm going to force the points to be here. Okay, to be perfect. Okay, so what do you see what's happening here? You have something that's a straight line in here, horizontal, but here it's not a straight line. Now, what is this? Because this is 3 and this is 5. What's going to be the value here of this area? This is going to be 15, right? Now, in this graph, what is 15? This is 5, this is 10, this is 15, because it's the graph of the space. So, if you do s of 3 minus s of 0, what's going to be s of 3? Well, this is 1, this is 2, this is 3. S of 3 is 15, minus s of 0 is right here, it's 0. It's 15. So you see that when you take the antiderivative, just this value right here represents this entire area in the function of the derivative. Okay, so a single value, it's not going to be the entire area of this thing here, no. Okay, a single value, for example, x, let's say x, f of d. Let's say that x equals d. A single value in the integration is going to be equal to the area underneath the graph of the derivative. Okay, that's going to be the area underneath the graph of the derivative. All right, from d, because this is d and it's starting at 0, so it's going to be from d. This is going to be from d, from 0 to d. You can say from 0, from 0 all the way to d. Okay. So this entire area here, you can represent it with a single value in the integration. All right. So this is an important relationship too. And that's it, guys. That's it. You can also see something else. Let's make something. I'm gonna show you guys like an example here. Let's see that you have a velocity that's changing. Okay, So the velocity is 2x. The velocity with respect to t, it's not 2x, it's 2t, okay? What's going to be the space of this? The space is going to be the integration of this with respect to t, which is 2t squared divided by 2. You cancel these, t squared, okay? So it's going to be t squared. Now look at that. You have a graph where the velocity, this is t and this is the velocity. The velocity is going straight up like this, okay? If the velocity is going straight up, the space is not going to go straight up. It'll go up like a parabola, okay? So here's t, and here you have the s as a function of t, okay? This is also a v as a function of t. So it'll go like this, kinda, okay? It's a curve. You see that? Okay, now which one is the derivative? This one is the derivative, this one's the integral, okay? Now, you see that, let's just say that this is 3, okay? This is just an example, guys, it's just an example. This is 3, and this here is also 3. 3 seconds here, 3 seconds here. Where is the derivative? This is the derivative. So the area underneath in here, okay, is going to be this single value in here. Let's just say that this whole thing is, well, 2 times 3 is 6, right? Yeah. So, now hold on. 3 seconds, okay? So at 3, it's going to be 9. So, at 3, what's going to be the space function in here? The space function is t squared. So this thing, what is this point in the Cartesian plane? Is 3, 9, okay? So this 9 is just a single value in the integration. If it's a single value in the integration, equals the entire area in this is going to be equal to the entire area in the differentiation graph. So I'm going to recap this again because I'm just getting sleepy. A single value in the graph of the integration equals the entire area under the graph of the differentiation. Okay, now let's see if it is for real. All right, I just said that this is 9, so this whole area here has to be 9. All right, now do you think it's 9? Well, let's see. During 3's, what's gonna be this height over here? This is the value of the function, right? So if it's 3 seconds, this height over here is gonna be 6. So this is the point 3, 6, right? All right. Now you guys can see that this is a triangle. Okay, what's gonna be the area of a triangle is the area, well, it's going to be the base times the height divided by 2. What's the base in here? It's 3 times the height. What is this height here? It's 6 divided by 2. 18 divided by 2 equals 9. See, the area here is 9. You got just one point in here in the integration graph, which is 9. So that's it, guys. Okay. Yeah, for now that's it. Yeah. Now, well, I just want to complicate things a little bit more, because let's just say you got this area here. But what if you want to find out this area here underneath this graph? Okay. This doesn't make any sense physically, but let's just say that you want this entire area in this graph. What do you have to do? You have to integrate. You're going to integrate the function of t, of the space as a function of time with respect to time. You're going to find out, let's just say that the integral of this is called gt, okay? So if you want to find out this area, you would do d of 3 minus g of 0. Now g of 0, we can see here that's just 0, right? So forget about that. And you will get the g of 3, and you would find out this area here, okay? So that's it, guys. I know it's confusing. You probably think, oh my god, this is a mess. But it is a mess. It's complicated. It takes a lot of intuition. You have to visualize the animation in your head of the widths of those rectangles becoming smaller and smaller and smaller and smaller and smaller. If you have, you know what I do to help me? I go like, okay, let's just say that I have a velocity here, and this is 3 seconds. Let's just say that this velocity equals 1, okay? So what do I have? I have a 1 times 3, so it's 3. But let's just say that the velocity is doing this, okay? How am I gonna know? It's becoming messy here. Okay. Let's just say that the velocity is doing this. It's increasing and decreasing. How am I gonna know? Well, get the velocity here, plus the velocity here, plus the velocity here, plus the velocity here. If you keep adding all these velocities, these instantaneous velocities, if you could do that in your mind, okay, infinitely, I'm gonna keep adding. What are you gonna have? You're gonna have in the end a space. You're not gonna have a velocity, okay? Try to think about this example in your mind. If you have a velocity of 3 plus a velocity of 4 plus 1.2 point something, because what do you have in here? You have a velocity of 1 for 1 second, and then you have a velocity of 1 for another second, and you have a velocity of 1 for the third second. So you have 1 plus 1 plus 1 equals 3 what? 3 feet per second? No, you 3 feet, because you're going at 1 feet per second for 3 seconds. So you go 1 feet in the first second, you go another feet in the second second, you go another feet in the third second, and in the end you have 3 feet, all right? Now, you see, let's just say that these velocities are not steady, they're not straight like this. They're going around like that, you know, and increasing and decreasing and decreasing. Let's just say that for this small amount of time in here, you could get that velocity. So it's gonna be that velocity plus the second velocity plus the third plus the fourth, and you're gonna have infinite velocities. And these velocities are gonna be measured for a very small amount of time, okay? It's not a delta t like this big. It's a delta t that's invisible, like this, you know, like a little thing of nothing. And then you calculate the velocity there, and you calculate the velocity here, and you calculate the velocity here. Add all these velocities, you will have the space in the end. That's strange. Adding velocities, you're not getting a final velocity, you're getting a space, okay? So that's the idea. And that's it, guys. At this point, if you can imagine these things happening, that's great. If you cannot, I'm really sorry, okay? The first time that I tried to make sense of this stuff, I was walking around my living room for 6 hours, maybe 9 hours, walking back and forth, because I think better when I walk. So I was walking back and forth trying to understand why, when you have the integral of a velocity with respect to time, you actually get a space function as a function of time. Why, when you do this, you get that, and how can you add a bunch of velocities and end up with space? How come you don't get a final velocity? I mean, if you're adding 1 feet per second plus another, you should have 3 feet per second, right? No, actually you're going to have 3 feet. That feet per second is just how much you went for that second, and then how much you went for the second second, okay? But try to imagine that these times are not 1 full second. It's something very tiny, and you're going just that much, like 5 feet per second in here, and in the second one you go 3 feet per second, and in the second one you keep adding all those velocities. In the end, you're gonna have a space. which is how much you went for each little particle of time, okay? So that is the idea. That's it, guys. That's it for this video.